So now we get to finding the volume of a solid obtained by rotating the region, right? So what do they give us? Let's just try out like 4x is equal to y squared. X is equal to 0, and maybe y is equal to like 10. Yeah?
X equals to y squared, x is equal to 0, and y equal to 10.
Yep. So I'm going to draw this out a little bit again. And I'll go ahead and draw in the x is equal to 0 and y is equal to 10, because those aren't too crazy, right? But x is equal to 0 is like this boundary. Y is equal to 10 is sort of like this boundary. And now we just want to draw 4x is equal to y squared. And from our discussion from before, what kind of parabola does this look like?
It should be like concave to the right.
I agree, concave to the right. I think it goes right through 0, 0. So it looks to me like the area in question is probably, let me erase some of this stuff. It's this one right here. Yeah. And they're asking us to revolve this region. Okay. They're asking us to revolve this region around the y-axis. They're asking us to revolve it around the y-axis. So that's going to look kind of like a, can you imagine? It's going to look like kind of like a cone, but like with a weird sloping side. Can you picture that?
I can picture it. I just never thought of it as that.
Okay. Yeah. So do you have any comments at the moment before we start discussing on how to actually calculate this? Because this is where we start getting into the circles and introducing the squaring of our variables that you mentioned before.
Is this method?
This is basically the disk method. Yeah, that's exactly what we're going to do. The disk. Rotating the region bounded by the given curves about the y-axis. Yes, okay. Yeah, no, that's exactly what we're going to do. What's up?
How do you know it's the disk method? Like, what pops in your brain when you see a question like this and you immediately know
when I'm being told, that's a great thing. That's a great question. So when I'm being told that I'm revolving a region around a specified line, the fact that I'm revolving it instantly makes me think disks.
Oh, okay.
Right?
So specific wording.
Yeah, the fact that it says revolve is a pretty big hint to use a disk. I think. Now I'm going to be scared that there are going to be exceptions, but I think that's an okay rule of thumb. Just remember that thumbs can be broken, like my math teacher used to say. But
my thumb broke.
I'm sorry to hear that. That's a really unfortunate coincidence. But the point is, if you don't want to rely on hints like this, then just always ask yourself, like, literally, what is happening here? And just to sort of draw it again, it's like saying, okay, we've got this shaded in region over here. It looks kind of like this, almost not quite a triangle. But if we're revolving it around the y-axis, well, the idea is, if we're revolving this around the y-axis, then every single one of these would-be rectangles now gets sort of spun around into a disk of infinitesimal height. You see that? What used to be a rectangle in one dimension is sort of now being spun around into a circle. Can you picture that? Is that crazy? Or is that easy to visualize?
It's easy to visualize. It's just like
tough, right? Gosh, I've forgotten what our equation is. So this line is 4x is equal to y squared. So x is equal to y squared over 4. You still there, buddy? Okay. So now I'm going to write I'm sort of going to try to draw an arbitrary cross-section, right? And what this is going to look like is essentially, just like I said, I'm going to try to draw it a bit neater than before, but this is going to be like a circle. This is going to be a very tiny, very thin cylinder, rather. This drawing isn't great, but you see what I'm trying to do here? Is this part is the circle. This is the circular base of the cylinder. And then in addition to that, there's also like this tiny little height to it. You see that? I'm not an artist, but can you see that? Can you see what I'm trying to draw here?
Yeah, I do.
Okay. So this right here is sort of like the dy, just the height right here. Whereas this circle part, we're going to try to find the area of. And the idea is if we can find the area of every single one of these cylindrical, if we can find the volume rather of each one of these differential little cylinders, then we can add those all up to find the volume of this entire thing. Can you like believe that? If we can just add up the volumes of all of these tiny little cylinders, we end up getting the volume of all the entire thing. Does that make sense?
The entire thing.
Yeah.
What do you mean by the entire thing?
Well, the entire thing is this like kind of Beyblade looking thing, right? The entire thing is like this giant Beyblade, and that's what we're trying to find the volume of. And to do that, calculus lets us sort of approximate it by breaking it up into a ton of these tiny little cylinders, right? These cylinders are all over the place and can have varying radii. But the idea is that if we add up a bunch of these things, we start to get a decent approximation for the volume. You see what I mean?
Yeah.
Yeah. And remember, this is totally analogous to that situation from before where we were adding up tiny little rectangles to get an area, right? We were adding up differential areas to get a total area. Now we're adding up a tiny little volume, or lots of tiny little volumes, to get a total volume. See the analogy? It's just sort of like a higher dimensional thing of what we've been doing in the past. But it trips people up because it's kind of tough to visualize. But mathematically, it's just exactly what we were doing before for area, now just with a volume. You see that?
Yeah.
Okay.
I see the difference. And then cross section is just going to be the area.
Yes, exactly. So I was just about to get to that. But the basic idea here is that, okay, so the idea here is that, how do I put it? If we sum up, let me write it this way. The idea is if we sum up each of these differential volumes, dV means like each dV is the differential volume of one of these cylinders. And it's a differential volume because even though it has a nice big circle with some area A, the height is infinitesimal. It's a dy. So that's why we call it a differential volume, because it's sort of A times the dy. You see that? Where this is just area of the circle. Okay? The area of a circle we just know is pi r squared. Yeah? And for this particular problem, r is just equal to x. So let me write that as the integral of pi x squared dy. Except for now, we want to rewrite x in terms of y because we're integrating with respect to y. Right?
That makes so much sense.
Makes so much sense. I'm so happy to hear you say that. You don't know how happy that makes me as a not quite educator, but random guy that likes teaching math. So we have x is equal to y squared over 4. I'm not even thinking right now. I'm just plugging this straight in over here. Right? So I'm saying the integral of pi y squared over 4 squared dy. And again, you told me that this ranges from, was it 0 to 10?
Mm-hmm.
I think you told me that, right?
Yeah.
Yeah, it's 0 to 10. Yeah. And gosh, like this is one of those integrals that you know how to solve from like the first day of Calc 2, right? At this point, it's just a big fat polynomial. And those are like the easiest ones to solve. You see this process? Step by step, we really want to, let me put it this way. Once you can get a comfortable grasp of what the heck an infinitesimal, this infinitesimal cylinder is, or it doesn't have to be for this particular, so the cylinder is for this particular type of problem, but once you can get a grasp of whatever your infinitesimal object is, be it an infinitesimal cylinder or an infinitesimal washer or whatever, once you can understand that infinitesimal you can just say, okay, I'm going to take that infinitesimal area, and this integral is just saying I'm adding up all of those infinitesimals, right? And then you just rewrite the dv as something you know how to calculate pretty easily, which is just area, right? That's something that's nice, finite, you can calculate it. And product of area and dy, where dy is sort of doing all of the calculus work, so to speak. Yeah. And from there, you just plug things in. You plug in, plug in. And once you have everything in terms of y, or everything in terms of the integration variable, just integrate. Sit back and relax. Yeah. It seems like so many people just, their idea of calculus 2 is that this pi x squared just comes kind of like out of nowhere, right? Like, I think so many people who are scared of calc 2 just feel like, oh my God, you know, disks, washers, where the hell do these pi's and squares come from? Pi's and squares come from. But like, if you can visualize it and figure out what you're actually adding up and express that in terms of our calculus notation, it suddenly becomes extremely formulaic, right? There. So what we did here was we sort of did a typical washer. Sorry, is this a disk? Sorry, this was a typical disk.
Yeah, a washer would have like a space in between.
Yes, a washer is a like a sort of a ring. Or if you want to sound like sophisticated, you call it an annulus. Yeah, it's for only for sophisticated mathematicians call it that. I call it a ring. Yeah, it's weird. That's at a certain point in math, every just mathematician suddenly starts referring to it as an annulus. It's like, this is a fucking conspiracy. What? Anyways, do you like propose to your partner with a wedding annulus? It's anyways, enough math jokes. Okay,